Hello everyone, I'm Chen Wang, currently a postdoc at Harvard. Today, I'm excited to presenting our study, Drava, Align Human Concepts with Machine Learning Latent Dimensions for the visual exploration of small multiples. Visual exploration of small multiples can be a challenging task. A common practice is to project them into a 2D space by learning a latent dimension for each item and then applying dimension reduction methods. This approach has been used in many visual analytics tools, and I just name a few here. The increasing popularity of embedding plots is also reflected in the Google Trends for Disney dimension reduction methods. Where embedding plots can reveal interesting patterns, they may not always be sufficient to guide the visual exploration. When projecting items into a 2D space, it's common to expect them to form clusters based on their similarity. But what if there is no clean clusters? What if the users are interested in certain aspects rather than the overall similarity? For example, each item on the right side is an image page from the breast cancer specimens. Interpreting the embedded plots of those items can be challenging. It is worth asking, can we go beyond clusters in visual exploration? How about looking at concepts? A concept is an abstraction that describes the characteristics of items, such as shape and texture. For example, a zebra is related to the concepts of horse and stripes. A concept can be shared by multiple classes. Therefore, a concept is a flexible and transformable form of knowledge that can guide visual exploration. Returning to the example of breast cancer specimens, a more interpretable visual exploration can be achieved by arranging the items based on two concepts, tissue density and tissue color. Concepts can be learned by a ML model, but the learned concepts usually exist in the latent space. They must be extracted and present to the users. This entangled representation learning is a promising method to achieve this goal. The model aims to disentangle concepts and encode them in separated latent dimensions. For example, the value of the second latent dimension is related to the angle of human head. By changing the value of this dimension, we can see that the head angle gradually changed in the synthesized images. Therefore, this entangled representation learning can learn concepts without labels, and more importantly, showing users what a concept looks like. For example, the concept of human heads, or the value of the second latent dimension, can be used to guide the visual exploration of human face images. Even though promising, those concepts cannot be directly applied due to the mismatch between humans and ML. For example, we can see here, the machine learning model confused the angle of the head with whether a part of the face is covered. To support concept-driven visual exploration, it is needed to present the concepts in a way that users can easily interpret, identify the potential mismatches, and provide feedback. Drava is designed to support concept-driven visual exploration by enabling users to interpret and steer concepts effectively. I will demonstrate the functionality using TAD, topological associated domains, a region of interest in genomic interaction matrix. You can think of each TAD as a heat map visualization, where the visual appearance represents biological events. First, interpret concepts. The most straightforward way to interpret concepts is through synthesized images associated with each concept. Drava represents each latent dimension as a row and ranking them by a salience score. We can see that there are three meaningful concepts with high rankings. Let's take a closer look. Those visual concepts are related to the biological events for the genomic interaction matrix. The synthesized image are intuitive. but may hide the concept mismatches between human and ML. Therefore, Drava also allows users to interpret concepts through items using interactive piles. Interactive piles is inspired by the efficiency of physical piling for grouping and summarizing items. For example, this pile is a group of similar tests, and this pile includes several abnormal items. Drava offers a range of piling interactions based on the item characteristics. For more details, please refer to our paper. Second, align ML with humans. Item piles can effectively reveal the concept mismatch between humans and ML. For example, here, the abnormal items shows that the ML model confused two concepts, the diagonal thickness with the nested structure. This mismatch can be hidden if we only look at the synthesized images, which unfortunately is widely used as the only method to present the concepts in disentangled representation learning. Since we have identified another dimension that is related to the diagonal thickness, we can use it to separate the abnormal items. Here, I use a nozzle to select those abnormal items and move them to the left side. By doing this, I'm telling the ML model to refine the concepts of those items. And this is one example of the various user refinements provided in Drava. After user refinements, an additional concept adapter is initialized to refine the learned concept, where we keep the original encoder and decoder fixed. The evaluation shows that the proposed method improves the concept quality compared to an active learning baseline. Third, generate new knowledge from concept-driven visual exploration. Let's revisit the breast cancer specimens example we discussed at the start of the talk. After arranging all the items based on tissue density and tissue color, we add item labels, which shows a strong correlation between the presence of cancer cells and those two concepts. We can further filter out items to investigate items that make the classification model generate confident but false negative predictions. We can see that those remind items are mostly loose purple tissues, and the spatial view shows that they are likely fat tissues surrounded by cancer cells. This observation can help us diagnose and refine the cancer classification model. In conclusion, Drava provides an interpretable and effective approach for data analysis by supporting concept-driven visual exploration. To achieve this goal, Drava combines disentangled representation learning with interactive visual piles, which helps users interpret concepts, identify mismatches, and generate insights. Please refer to our homepage for more details. Thank you for listening to my presentation. I welcome any questions and comments you may have.